Every rocket ever launched obeys the same mathematical relationship. Every spacecraft that ever left Earth paid tribute to the same formula. This equation does not care about your funding. It does not care about your ambition. It does not care about breakthroughs or genius or willpower. It scales punishment faster than any technology can compensate. For every kilogram you want to send deeper into space, the equation demands exponentially more fuel. And the fuel to carry that fuel demands more fuel still. This single relationship, discovered over a century ago, quietly governs everything humanity can accomplish beyond Earth. It defines the ceiling of our cosmic reach, and most people have never heard of it. If you want to understand the true limits of space exploration, hit that like button and subscribe. Let's begin. Picture every rocket launch you have ever witnessed. The thunderous ignition that shakes cameras positioned miles away from the pad. The pillar of flame erupting from beneath the vehicle, painting the surrounding clouds in shades of orange and gold. The impossible spectacle of thousands of tons rising against gravity, climbing on a column of fire toward the black emptiness above. The roar that reaches observers seconds after ignition, rolling across the landscape like sustained thunder. Now, understand something that changes everything about what you just witnessed. 90% of that towering machine is fuel. The spacecraft itself, the crew capsule where astronauts sit strapped into their seats, the scientific instruments designed to study distant worlds, the life support systems that will keep humans alive in the vacuum, the computers that guide the vehicle through its trajectory, the food and water packed for the journey, all of it amounts to a sliver of the total mass sitting on the launch pad. The overwhelming majority of that vehicle, that engineering marvel representing decades of human effort and tens of billions of dollars in development, exists only to burn and be thrown away. Look at that rocket differently now. See it not as a spacecraft with fuel attached, but as a towering column of propellant with a tiny spacecraft perched on top. The vehicle you admire is mostly a flying fuel tank. The part that actually goes somewhere useful, the part that accomplishes the mission, represents a fraction so small it would disappear if you tried to see it from a distance. This is not a temporary problem awaiting a clever solution. This is not an engineering challenge that better materials will eventually overcome. This is not something that more funding or smarter scientists or revolutionary technologies will fix. This is physics, and it emerges from a single mathematical relationship that governs everything humanity has ever accomplished or ever will accomplish in space. Most people assume that space travel is difficult primarily because of distance. They imagine the challenge as one of crossing vast gulfs, of building vehicles capable of traveling far. With enough funding, enough determination, enough technological progress, we could eventually reach anywhere in the cosmos. The Moon required massive rockets. Mars will require bigger ones. Jupiter's moons will need something larger still. Eventually, the thinking goes, some breakthrough will make everything easier. Rockets will become like airplanes. Space travel will become routine. Our grandchildren will vacation on orbital hotels and commute to lunar mining facilities. This assumption is catastrophically wrong. The difficulty of space travel does not scale linearly with distance. It does not even scale reasonably with distance. It scales exponentially with the velocity changes required. And the reason traces back to one equation discovered by a deaf Russian schoolteacher working in complete isolation more than 120 years ago. In 1903, in a provincial Russian town called Kaluga, far from any center of scientific activity, far from the universities and academies where physics was being revolutionized, a man named Konstantin Tsiolkovsky sat alone with his calculations. He had been deaf since childhood, the result of scarlet fever that robbed him of his hearing at age 10. This disability had forced him into a life of solitary study. He could not follow lectures. He could not participate in the vibrant scientific discussions of his era. He could not hear the debates about the nature of space and time that were transforming physics in the great universities of Europe. Instead, he taught mathematics in local schools. He earned modest wages that barely supported his family. He lived in a small wooden house and spent his evenings contemplating a question that seemed absurd, even laughable, to his contemporaries. How might humanity travel to the stars? The question itself marked Tsiolkovsky as an eccentric, a dreamer disconnected from practical reality. In 1903, when Tsiolkovsky published his work, the Wright brothers had not yet made their historic flight at Kitty Hawk, which would come later that same year in December. Powered heavier-than-air flight remained a fantasy that most serious scientists considered impossible. The notion of travelling beyond Earth's atmosphere, of reaching other worlds, belonged to the realm of fiction and fantasy. Working entirely from first principles, he applied Newton's laws of motion to a theoretical vehicle that would expel mass to generate thrust. He had no experimental data to guide him. He had no colleagues to check his work. He had only mathematics, logic, and an imagination that refused to accept the boundaries his contemporaries assumed were permanent. What he discovered would define the limits of every space program that would ever exist. Tsiolkovsky never built a rocket. He never launched anything into space. He never saw a spacecraft or witnessed a launch or met another person seriously working on space travel. He died in 1935. Just as the first primitive liquid-fueled rockets were proving that his theoretical work had been correct all along, he never knew that his equation would govern the Apollo program, would constrain the space shuttle, would determine the size of every launch vehicle humanity would ever build. The equation he derived describes something that seems simple at first glance. A rocket accelerates by throwing mass out the back. Push something backward, and you move forward. Expel exhaust gases at high velocity, and the vehicle accelerates in the opposite direction. The faster you throw that mass, the more thrust you generate. The more mass you throw, the longer you can accelerate. This is straightforward physics. What makes it devastating is the feedback loop that Tsiolkovsky recognized and captured in mathematical form. The fuel a rocket carries adds to the mass that must be accelerated. This seems obvious when stated directly, but its implications are profound. To carry more fuel, you need more fuel to lift that additional fuel. To lift that additional fuel, you need still more fuel. To lift that fuel, you need yet more. This creates a compounding relationship that grows without bound, a feedback loop that consumes itself. Every kilogram of propellant you want to burn later must first be accelerated by propellant you burn now. That propellant you burn now must have been accelerated by propellant you burned earlier. The weight of your future burns determines how much you must burn in the present. The weight of your present burns adds to what you must have burned in the past. Tsiolkovsky captured this relationship in mathematics that haunts every rocket engineer who has ever lived. The velocity change a rocket can achieve relates to two quantities: the exhaust velocity of its engine and the ratio between its initial mass and its final mass after burning all propellant. The exhaust velocity describes how fast the engine expels its combustion products. The mass ratio describes how much of the rocket consists of propellant versus everything else. But here is where human intuition fails completely. That mass ratio appears inside a natural logarithm, which means the required starting mass grows exponentially with the desired velocity change. This single mathematical fact changes everything about what rockets can accomplish. To achieve twice the velocity change does not require twice as much fuel. It requires fuel multiplied by fuel. The mass ratio squares. To achieve 3 times the velocity change requires that already enormous number multiplied again. The mass ratio cubes. 4 times the velocity change demands the 4th power. Small increases in required velocity demand staggering, incomprehensible increases in starting mass. The penalty escalates faster than human intuition can grasp. Our minds evolve to understand linear relationships. We expect that twice the effort produces twice the result. 3 times the investment yields 3 times the return. This expectation serves us well in daily life, where most relationships are approximately linear over the ranges we experience. The rocket equation violates this expectation catastrophically. Consider what happens when you ignite a rocket engine and begin the climb towards space. At the beginning of the journey, the vehicle groans under the weight of its propellant load. The tanks are full. The mass is enormous. Every newton of thrust must push not just the spacecraft and its payload, but all the fuel the rocket still carries. The acceleration is sluggish, ponderous. The rocket rises slowly, fighting against both gravity and its own tremendous weight. As the engine fires, propellant burns away. Combustion products blast out the nozzle at kilometers per second. The tanks gradually empty. The vehicle becomes lighter. Thrust that struggled to lift the initial mass now pushes against substantially less. The rocket accelerates faster and faster as it empties itself. The ride becomes more violent as the thrust-to-weight ratio improves. Astronauts feel themselves pressed harder into their seats as the vehicle sheds its burden of propellant. This sounds efficient. It sounds like the rocket is getting better at its job as it progresses. It sounds like a system that rewards progress and improves with time, until you realize what it means in reverse. To accelerate that heavy initial mass at all, you needed far more propellant than you will eventually use for actual velocity change. Most of the fuel exists only to accelerate other fuel. The propellant burned in the first seconds of flight accomplishes almost nothing except lifting the propellant that will be burned in subsequent seconds. That propellant in turn exists largely to lift propellant burned still later. The payload, the actual useful mass you wanted to send somewhere, represents a shrinking fraction of the total. The more velocity change you require, the smaller that fraction becomes. At some point, the fraction becomes so small that no practical rocket can achieve the mission. The payload disappears into a rounding error, crushed beneath the exponential weight of all the propellant needed to move it. The German engineers who built the V-2 rocket during World War II discovered this constraint the hard way. They were trying to deliver explosive warheads to targets hundreds of kilometers away. Their missile required approximately 9 tons of propellant to deliver a 1-ton warhead over its intended range. The ratio seemed wasteful, inefficient, surely improvable with better engineering. It was not improvable. The ratio emerged from physics, not from engineering limitations. Better pumps and lighter structures and more efficient combustion chambers could shave percentages from that ratio. They could not fundamentally change it. The equation permitted nothing dramatically different. When American and Soviet teams captured German rocket technology and personnel after the war, they began expanding upon those foundations. They built bigger rockets with more capable engines. They developed new propellant combinations that burned hotter and faster. They refined manufacturing techniques and reduced structural mass percentages. They accumulated decades of experience and billions of dollars in investment, and still they encountered the same mathematics. Every design, every proposal, every ambitious plan ran headfirst into the same equation Tsiolkovsky had derived in his wooden house in Kaluga. The relationship he captured proved universal. It did not matter which country built the rocket. It did not matter what political system funded the program. It did not matter how talented the engineers or how generous the budget. The equation applied equally to all. The engineers who designed the Saturn V to reach the moon faced identical constraints. They did not find clever ways around the equation. They did not discover loopholes that Tsiolkovsky had missed. They accepted its verdict and built accordingly. Constructing a vehicle whose size was determined not by ambition but by mathematical necessity. That rocket stood 36 stories tall, the height of a substantial office building. It weighed nearly 3,000 metric tons at launch, more than a fully loaded freight train. It produced 7.5 million pounds of thrust at liftoff, more than any vehicle before or since. It remains the most powerful rocket ever successfully flown. The command module that actually travelled to the moon and back, the capsule where 3 astronauts lived and worked during their journey, weighed about 5.5 metric tons. The ratio between launch mass and returning spacecraft approached 600 to 1. 600 pounds of rocket for every pound that came home. Those proportions were not mistakes. They were not inefficiencies waiting to be corrected by future engineers with better ideas. They represented the rocket equation's verdict on what reaching the moon and returning actually required. Every kilogram of the command module demanded hundreds of kilograms of propellant and supporting structure. Every piece of equipment the astronauts carried had been weighed against the exponential cost of lifting it. The numbers could not have been significantly different with the technology available in 1969. They will not be dramatically different a century from now, as long as the laws of physics remain unchanged. What makes Tsiolkovsky's equation so powerful, so inescapable, so fundamentally constraining, is its universality. It applies regardless of propellant type. Burn hydrogen and oxygen, the highest performing chemical propellant combination known. Burn kerosene and oxygen, cheaper and denser, but less energetic. Burn hydrazine or nitrogen tetroxide or exotic combinations that require cryogenic storage and special handling. It governs all of them equally. Different propellants produce different exhaust velocities, which affects the numbers, but the fundamental exponential relationship remains intact. It applies regardless of engine design. Build engines with turbopumps that feed propellants at enormous pressures. Build engines with pressure-fed systems that trade simplicity for performance. Design combustion chambers of any geometry, nozzles of any expansion ratio, cooling systems of any configuration. The equation remains unchanged. Every engine that expels mass to generate thrust must answer to this same arithmetic. It applies regardless of destination. Travel to low Earth orbit, a few hundred kilometers above the surface. Journey to the moon, nearly 400,000 kilometers away. Voyage to Mars or Jupiter or Saturn or the frozen reaches of the outer solar system. Farther destinations that demand more velocity change face exponentially harsher penalties. The equation does not care about ambition. Political leaders can declare bold visions of human expansion into the cosmos. They can allocate billions of dollars and mobilize armies of engineers. They can inspire generations of young people to pursue careers in aerospace. The equation responds to none of this. It does not bend to political will or public enthusiasm, or the dreams of children gazing at the stars. Kennedy's deadline for reaching the moon did not change what the mission required. Budget pressures and schedule constraints exist in the human world. The equation exists in the physical world, indifferent to both. It simply describes how the universe works. And the universe makes space travel fundamentally difficult. Consider what this means for the most basic challenge of spaceflight, reaching orbit around Earth. A spacecraft sitting on the launch pad exists at the bottom of a gravitational well. Earth's gravity pulls everything toward the center of the planet with relentless force. To reach orbit, a vehicle must accelerate to roughly 7.8 kilometers per second, fast enough that the curve of its fall matches the curve of the Earth below. At that speed, the spacecraft is technically falling, but it falls around the Earth rather than into it. 7.8 kilometers per second. About 17,500 miles per hour. More than 23 times the speed of sound at sea level. That is the velocity required simply to stay up, to maintain a stable orbit a few hundred kilometers above the surface. But that number represents only part of the challenge. The rocket must also fight against gravity during the entire ascent. Every second of flight, gravity pulls downward on the vehicle, subtracting from the velocity the engines add. This gravity drag consumes significant amounts of the rocket's capacity. The vehicle must also push through the atmosphere during the critical first minutes, losing still more velocity to air resistance. The trajectory is never perfectly efficient, requiring additional velocity to account for steering losses and non-optimal flight paths. When you account for gravity losses during ascent, atmospheric drag through the lower atmosphere, and the realities of any achievable trajectory, the total velocity change required to reach low Earth orbit approaches 9.5 kilometers per second. This represents the entry fee for reaching space. You cannot get to orbit with less. Every rocket, regardless of design philosophy, no matter how brilliant its engineers or how generous its budget, must produce this much velocity change to deliver anything to orbit. 9.5 kilometers per second is the price of admission. Pay it or stay home. Modern rocket engines exhaust combustion gases at velocities between 3 and 4.5 kilometers per second. Depending on propellant type and engine design, hydrogen-oxygen engines achieve the highest exhaust velocities. Hydrocarbon-oxygen engines produce lower exhaust velocities but offer other advantages in density and cost. When you apply the rocket equation to these numbers, the mass ratio required becomes severe. A typical rocket must begin its journey weighing 15 to 25 times what it weighs after reaching orbit. For every ton that achieves orbital velocity, 15 to 25 tons must sit on the launch pad at ignition. The overwhelming majority of that mass is propellant that will be consumed during the 8-minute climb to space. This is why rockets look the way they do. Those towering structures, sitting on launch pads around the world, are not monuments to human ambition. They are not celebrations of our power to reshape nature according to our will. They are monuments to mathematical constraint, physical confessions of our inability to escape exponential penalties. When you see a rocket carrying astronauts to the International Space Station, understand what you are actually seeing. The spacecraft itself, the capsule where humans sit, and the service module that supports them represents roughly 5% of the launch mass, sometimes less. 95% of the vehicle consists of propellant and the tanks and engines and structures needed to contain and burn that propellant. The crew capsule is a rounding error on the total system. These numbers emerge not from inadequate engineering but from physics itself. The best rocket scientists in the world, with unlimited budgets and decades of development time, still produce vehicles dominated by propellant mass. They shave grams wherever they can, arguing over the weight of bolts and brackets and wire insulation. They optimize every weld and every fitting, seeking structural efficiency at the margins. They use exotic, lightweight materials that cost thousands of dollars per kilogram, materials developed specifically to save weight on spacecraft, and still their rockets consist overwhelmingly of fuel. They have no choice. The equation permits nothing else. This brings us back to the equation, to that simple-looking relationship derived by a deaf schoolteacher more than a century ago. Every mission that ever flew answered to this same arithmetic. The triumphant moon landings that inspired a generation. The robotic probes scattered throughout the solar system, visiting every major planet and many smaller bodies. The space shuttles that promised routine access to orbit but never delivered on that promise. The International Space Station, assembled piece by piece over decades. Every Falcon that lands on a drone ship, and every Soyuz that climbs from the steppes of Kazakhstan, all of them pay the same tax imposed by exponential mathematics. The equation operates silently behind every space achievement, extracting its toll without acknowledgement. News coverage shows the spectacular hardware and celebrates the human accomplishment. Documentaries depict the drama of countdown and launch, the tension in mission control, the relief when spacecraft reach their destinations. They rarely mention the mathematical relationship that determined the size of that hardware and constrained what it could accomplish. Understanding this equation fundamentally changes how you see space exploration. Those massive rockets are not symbols of human power over nature. They are confessions of our powerlessness against mathematics. Their size reflects not our strength but the severity of the penalty physics imposes on any attempt to leave Earth. The rockets that carry communication satellites into orbit consume vast quantities of propellant to deliver payloads that weigh a few tons. The vehicles that transport astronauts to the space station require launching more than 20 times the mass that actually reaches orbit. The probes we send to other planets demand even more extreme ratios. None of this represents failure. None of it represents inefficiency that cleverer engineers could eliminate. It represents the best possible performance under an unbreakable law. Engineers have spent 70 years optimizing every component, reducing every unnecessary gram, increasing engine efficiency to within a few percentage points of theoretical limits. The rockets we build today operate remarkably close to what physics permits. Combustion temperatures approach what materials can withstand. Structural mass fractions approach what manufacturing can achieve. Trajectory optimization squeezes out nearly every available advantage. There is simply not much room remaining for improvement. This is the hidden truth of spaceflight that rarely appears in popular discussions of space exploration. The challenge is not primarily technological. Though technology matters, it is not primarily economic, though costs are enormous. It is not primarily political or organizational or sociological, though all of these factors affect what programs actually get built and flown. The challenge is mathematical. The rocket equation establishes limits that no amount of cleverness can truly overcome. It grants small victories to brilliant engineering while maintaining its fundamental dominance over what we can achieve. It permits incremental improvements while forbidding revolutionary changes. It says yes to some missions and no to others, based on arithmetic that admits no negotiation. The equation explains why space travel has remained so difficult for so long. After 70 years of continuous development, launching cargo to orbit still costs thousands of dollars per kilogram. After sending 12 humans to walk on the moon between 1969 and 1972, we have not returned since. After decades of promises about routine space access, reaching orbit remains an enormous undertaking, requiring months of preparation and accepting significant risk of catastrophic failure. Physics has always determined what is possible and imposed severe constraints accordingly, yet most people who dream of space exploration never learn about this equation. They absorb visions of the future from science fiction, where sleek spacecraft zip between planets like automobiles between cities, where starships jump to distant solar systems between commercial breaks, where the challenge of space travel is adventure and drama rather than relentless mathematical penalty. They assume that technology progresses inevitably toward easier solutions. They have watched computing power double every 2 years, watched the price of solar panels plummet, watched electric vehicles go from curiosity to commonplace. Surely rockets will follow the same trajectory. Surely someone will figure it out. Surely reaching Mars or the outer planets or eventually other stars simply requires continued effort and investment. The mathematics suggest otherwise. Certain difficulties are permanent features of space travel, not temporary inconveniences awaiting solutions. The universe imposes costs on movement through space that cannot be negotiated away. This is not what anyone wants to hear. We prefer stories of human ingenuity triumphing over obstacles. We celebrate the engineers who solve impossible problems. We believe that with enough creativity, any barrier can be broken, any limit can be transcended, any dream can become reality. The rocket equation presents a different kind of barrier. It is not a wall to be climbed or tunneled through. It is not an obstacle to be circumvented or overcome. It is the terrain itself. Every rocket ever built has operated on this terrain. Every rocket ever designed must account for its contours. No technology that obeys the same physical principles can escape it. This is the governor hidden inside every rocket. A quiet regulator that determines how far we can reach and how much we can carry. It operates in the background of every mission profile and every budget proposal. Engineers know it intimately. They live with it daily. Physicists accept it as fundamental, as unchangeable as the speed of light or the charge of the electron. But the public conversation about space exploration often proceeds as if this equation does not exist. The chapters that follow will examine how this single mathematical relationship shapes everything humanity attempts beyond Earth. We will see how it punishes ambition with exponential severity, demanding ever greater sacrifices for ever smaller gains. We will explore why proposed solutions fail to escape its constraints despite promising revolutionary improvements. We will confront what the equation means for the ultimate limits of human reach into the cosmos, but the essential understanding begins here. There exists a mathematical relationship, discovered more than 120 years ago by a deaf schoolteacher working in solitary isolation, that governs and limits everything humanity can accomplish in space. This relationship describes how rockets actually work, not how we wish they worked. It extracts an exponential toll on every velocity change, demanding more mass than intuition suggests possible, crushing payload fractions beneath the weight of propellant needed to move them. This is the hidden governor of space exploration. It permits some things and forbids others. It shapes the rockets we build and the missions we fly. It determines which dreams remain forever dreams and which can become reality. The equation does not negotiate. It does not compromise. It does not care about human hopes or fears or ambitions. It simply describes the universe as it actually is. And the universe, it turns out, makes space travel very, very hard. Every journey through space costs velocity, not money in the way accountants measure it, not time in the way calendars track it, not fuel as an abstract quantity to be purchased and loaded. Every journey costs specific amounts of velocity change that must be purchased with propellant mass, paid according to an exchange rate that grows more punishing with every increment demanded. This currency has a name that appears in every spacecraft design document, every mission proposal, every engineering analysis ever conducted for travel beyond Earth. Delta V. The Greek letter delta representing change, combined with V representing velocity, change in velocity, the fundamental unit of what spacecraft can accomplish. Delta V measures capability. It quantifies every maneuver a spacecraft might perform. Launching from Earth's surface to orbit requires a specific delta V expenditure. Transferring from low orbit to a trajectory reaching the Moon costs additional delta V. Slowing down to enter lunar orbit demands more. Landing on the surface extracts still more. Every course correction, every orbital adjustment, every change in trajectory requires spending from the delta V budget. When mission planners design spacecraft, they begin with delta V requirements. How much velocity change does this mission demand? The answer determines everything else. The propellant load follows from the delta V requirement. The tank sizes follow from the propellant load. The structural mass follows from the tank sizes. The engine thrust follows from the total mass. Every parameter cascades from that initial question about velocity change. The rocket equation converts each delta V requirement into a mass ratio. That mass ratio determines how much propellant must be carried relative to everything else. And here is where the mathematics become visceral, where the abstract exponential relationship translates into concrete engineering impossibility. Understanding delta V reveals why some missions remain practical while others border on impossible, why reaching low Earth orbit, while expensive, happens routinely, why reaching the Moon required the largest rocket ever built, why reaching Mars with human crews remains extraordinarily difficult, why reaching the outer planets with anything more than robotic probes borders on fantasy. The numbers do not scale kindly. They do not scale reasonably. They do not scale in any way that human intuition finds acceptable. Small increases in delta V requirements translate into dramatic, devastating increases in necessary mass. The exponential nature of the rocket equation takes abstract mathematics and transforms it into mission-killing reality. The entrance fee to space, as we have seen, costs 9.5 kilometers per second and demands a mass ratio approaching 16 to 1. For every kilogram delivered to orbit, 15 kilograms remain behind as burnt propellant and discarded structure. This tax applies to the finest rockets humanity has ever built. But reaching low orbit is only the beginning. The entrance fee merely gets you through the door. Moving beyond Earth, traveling to other worlds, requires additional delta V. and each additional increment demands another multiplication of mass, another compounding of the exponential penalty. But reaching low orbit is only the beginning. The entrance fee merely gets you through the door. Moving beyond Earth, traveling to other worlds, requires additional delta V, and each additional increment demands another multiplication of mass, another compounding of the exponential penalty. To escape Earth's gravitational influence entirely requires approximately 3.2 kilometers per second beyond orbital velocity. A spacecraft in low orbit, traveling at 7.8 kilometers per second, must accelerate to 11 kilometers per second to break free of Earth and travel outward into the solar system. That additional 3.2 kilometers per second does not come free. It demands propellant. That propellant has mass. That mass must be lifted to orbit in the first place. Traveling from low Earth orbit to a trajectory that reaches the Moon costs approximately 3.2 kilometers per second of delta V. The spacecraft must accelerate enough to climb out of Earth's gravitational well and fall toward lunar distance. Upon arrival at the Moon, the spacecraft must slow down to enter lunar orbit, costing roughly another kilometer per second. Landing on the surface demands approximately 2.1 kilometers per second more. The lunar module must cancel its orbital velocity and descend against the Moon's gravity. Each number feeds back into the equation. Each requirement demands more propellant, more structure, more mass at every preceding stage of the mission. The delta V budget accumulates, and the mass ratio grows exponentially with each addition. Here is where intuition fails most people, where the abstract mathematics collide with expectations shaped by everyday experience. Adding 3.2 kilometers per second to the 9.5 already needed might seem like a 35% increase in difficulty. If reaching orbit costs a certain amount of propellant, surely reaching beyond orbit costs perhaps 40% more. The relationship feels linear, because most relationships in daily life are approximately linear. The rocket equation says otherwise. Because the relationship is exponential, that additional 4 kilometers per second nearly doubles the required mass ratio. Not a 40% increase, not a 50% increase, nearly a doubling. A mission to the Moon cannot simply use a rocket 40% larger than one reaching low Earth orbit. It cannot use a rocket twice as large. It requires a vehicle many times larger, a tower of propellant and structure that dwarfs anything needed for orbital missions. The rocket must carry fuel to accelerate still more fuel. Each layer adding to the mass that all previous layers must lift. The Saturn V was not slightly bigger than contemporary orbital rockets. It was enormously larger. And that size difference existed precisely because the Moon mission demanded delta V that exponentially inflated the necessary mass. The full delta V budget for a complete lunar landing mission illustrates the compounding penalty with uncomfortable clarity. Launch to low Earth orbit costs 9.5 kilometers per second. The rocket must accelerate from 0 to orbital velocity while fighting gravity and atmosphere throughout the ascent. Translunar injection adds approximately 3.2 kilometers per second. The spacecraft must accelerate from orbital velocity to a trajectory that will carry it to lunar distance, climbing out of Earth's gravitational well. Lunar orbit insertion requires roughly 1 kilometer per second. Upon arriving at the Moon, the spacecraft must slow down enough to be captured by lunar gravity, rather than swinging past and returning to Earth. Landing on the surface demands 2.1 kilometers per second. The lunar module must cancel its orbital velocity and descend to the surface, using thrust to control the descent rate against the Moon's gravitational pull. Ascending back to lunar orbit costs another 2.1 kilometers per second. The ascent stage must accelerate from the surface back to orbital velocity, reversing the landing maneuver. Returning to Earth requires approximately 0.8 kilometers per second to leave lunar orbit and fall back toward Earth. Plus, mid-course corrections along the way. The total approaches 19 kilometers per second when you account for all maneuvers and reasonable margins for contingencies. 20 kilometers per second represents more than double the delta V needed for reaching low Earth orbit alone. The rocket equation does not treat this doubling of delta V as a doubling of difficulty. It does not even treat it as a quadrupling. It treats it as an exponential escalation that demanded the largest, most powerful rocket ever successfully flown in human history. 3,000 metric tons of vehicle to deliver 12 men to the lunar surface and return them safely to Earth. Consider what happens to the payload fraction as delta V requirements climb this exponential curve. Payload fraction measures how much useful mass a rocket can deliver compared to its total starting mass. It represents efficiency in the most fundamental sense. What fraction of all that propellant and structure actually accomplishes the mission objective? For a mission to low Earth orbit with a mass ratio of approximately 16, the payload fraction sits around 5 to 6%. 94 to 95% of the rocket consists of propellant and the tanks and engines and structures needed to contain and burn that propellant. Only 5 or 6% represents useful cargo delivered to orbit. 5% already seems remarkably low. A truck delivering cargo across the country does not consist of 95% fuel. An airplane flying passengers overseas does not discard 95% of its mass during the journey. But rockets must, because the equation demands it. Now apply those moon mission delta V requirements. Watch the payload fraction crash toward fractions of a single percent. The Saturn V delivered roughly 50 metric tons to translunar trajectory from its 3,000 metric ton launch mass. Less than 2% continued beyond Earth orbit. 98% remained behind as burnt propellant and discarded stages sacrificed to the equation's demands. And that 50 metric tons included the lunar module, the service module, the command module, and all the propellant those vehicles would need for the remainder of the journey. The astronauts themselves, the actual human beings accomplishing the mission, represented a rounding error on the total system mass. The mathematics punish ambition without mercy. Mars missions require delta V budgets that exceed the lunar mission by substantial margins. A complete round trip to Mars with landing and return demands delta V exceeding 25 kilometers per second, possibly approaching 30 depending on mission design and timing. Every kilometer per second beyond the moon mission requirement drives the mass ratio higher along an exponential curve that shows no signs of flattening. The mass ratios implied by Mars mission requirements make traditional approaches nearly unworkable with chemical propulsion. Engineering estimates suggest that landing 4 astronauts on Mars and returning them safely to Earth would require launching hundreds of metric tons to low Earth orbit. Not hundreds of metric tons launched directly to Mars. Hundreds of metric tons assembled in Earth orbit into a vehicle that dwarfs anything humanity has ever constructed in space. Some estimates exceed 1,000 metric tons of departure mass from low Earth orbit for a minimal human Mars mission. That mass must first be launched from Earth's surface, paying the 9.5 km per second tax on every kilogram. The total launch mass from Earth's surface climbs toward the tens of thousands of metric tons when you account for getting the mission hardware to orbit in the first place. These numbers do not reflect engineering conservatism or excessive caution. They reflect what reaching Mars and returning actually costs. The numbers can be adjusted through mission design changes. They can be reduced somewhat through clever architecture, but they cannot be made small through any clever trick. The outer planets present requirements that border on the absurd. Jupiter lies 5 times farther from the Sun than Earth. Reaching Jupiter orbit requires delta V substantially exceeding Mars requirements. A round-trip human mission to Jupiter's moons would demand delta V budgets that no chemical propulsion system can practically provide. The mass ratios grow beyond any reasonable capability. Saturn, Uranus, Neptune. These destinations lie so far from the Sun, require such enormous velocity changes to reach, that human missions using chemical rockets become exercises in mathematical fantasy rather than engineering analysis. The outer solar system remains closed to human exploration using any propulsion technology that operates on current principles. Spacecraft engineers cope with the exponential penalty through techniques that partially mitigate its severity. The most important technique is called staging. Instead of building one rocket that carries all its propellant from launch to destination, engineers construct multiple stages that fire in sequence and are discarded when empty. The first stage ignites at launch and burns until its propellant is exhausted. Then it separates and falls away. The second stage ignites and continues the acceleration, now pushing only the remaining stages rather than the entire original vehicle. When the second stage empties, it too separates. The third stage continues, pushing an even smaller remaining mass. Staging represents brilliant engineering insight. It recognized that carrying empty tanks and exhausted engines serves no purpose and extracts ongoing penalty from the equation. Discarding that dead weight improves the mass ratio of subsequent stages, allowing them to operate more efficiently. The Saturn V used this principle across 3 stages. The first stage, called the SIC, burned 5 massive F1 engines consuming kerosene and oxygen. It lifted the entire vehicle off the pad and accelerated it to about 2.7 kilometers per second before separating and falling into the Atlantic Ocean. The second stage, the S2, burned 5J, 2 engines consuming hydrogen and oxygen. It accelerated the remaining vehicle to near orbital velocity before separating. The third stage, the S4B, completed orbital insertion and later reignited to send the spacecraft toward the Moon. Each separation improved the mass ratio of subsequent burns. Each discarded stage removed dead weight from the equation's calculation. The technique transformed an otherwise impossible mathematical problem into merely a severe one. But staging does not defeat the equation. It merely delays the inevitable moment when mass ratios become unworkable. Each stage still obeys the same exponential relationship. Each stage still converts its delta V requirement into a mass ratio that determines its propellant fraction. Staging allows the stages to be optimized somewhat independently, but the overall system still pays the full exponential price. Adding more stages helps, but with sharply diminishing returns. Each additional stage brings additional complexity. Separation systems add mass. Additional engines add mass. Stage structures that must withstand the stresses of launch add mass. Interfaces between stages add mass. The staging system itself begins consuming the benefits staging provides. The mathematics prove this conclusively. An ideal rocket with infinite stages and no structural mass whatsoever could theoretically achieve any delta V with any payload fraction. This represents a mathematical limit that real rockets cannot approach. Real rockets with real structures, real engines, real separation systems, and real interfaces hit diminishing returns after 3 or 4 stages. Beyond 4 stages, the additional complexity, additional failure points, and additional structural mass outweigh any mathematical benefit from staging. The equation allows staging to help. It does not allow staging to escape. This is why the space industry has largely settled on 2 or 3 stage configurations for most missions. Further staging does not significantly improve payload fractions. 4-stage rockets offer minimal advantages over 3-stage designs while introducing substantial additional complexity. 5 or 6 stages provide essentially no benefit while dramatically increasing the probability of failure. The rocket equation has been optimized nearly as far as optimization can go. Engineers have extracted most of the available benefit from staging. What remains is incremental improvement, not transformative change. Every kilogram aboard a spacecraft carries what might be called the rocket equation tax. For that kilogram to reach low Earth orbit, approximately 15 to 20 kilograms of propellant and structure must burn and be discarded during ascent. The kilogram at destination cost 15 to 20 kilograms at launch. For that kilogram to continue beyond Earth orbit, several more multiplications of mass become necessary. Every additional maneuver adds to the tax bill. Every kilometer per second of additional delta V compounds the penalty. This tax applies to everything. Every wire running through the spacecraft, every bolt holding structures together, every circuit board processing data, every instrument collecting scientific measurements, every ration of food packed for astronaut consumption, every litre of water stored for drinking and hygiene, every component required for the mission multiplies through the equation. A kilogram of food for a Mars-bound astronaut does not cost merely 1 kilogram at launch. It costs dozens of kilograms, possibly hundreds, when you account for all the propellant needed to launch it, accelerate it toward Mars, slow it down at Mars, and potentially return the astronaut who consumed it. The tax on that food kilogram cascades through every stage of the mission. Spacecraft designers obsess over mass because of this tax. They build satellites from exotic lightweight materials that cost thousands of dollars per kilogram. They use honeycomb structures and carbon fiber composites. They mill aluminum to paper-thin dimensions. They spend months analyzing components to remove every unnecessary gram. They strip human spacecraft to minimum acceptable margins. Life support systems provide adequate but not generous air and water. Living volumes constrain crews to spaces that would feel cramped in a submarine. Every comfort and convenience must justify its mass against the exponential penalty it extracts from mission capability. Engineers argue over grams in components that will multiply into kilograms at the launch pad. They debate whether bolts can be made slightly smaller, whether brackets can use slightly thinner material, whether wire gauge can be reduced by 1 increment. These debates might seem obsessive, might seem to miss the forest for the trees, but each gram saved translates into multiple grams of propellant not needed, which translates into structure not needed to hold that propellant, which cascades through the system. This is not excessive caution. This is not engineering perfectionism run amok. This is rational response to exponential mathematics. When every kilogram extracts a toll measured in dozens or hundreds of kilograms at origin, mass reduction becomes the dominant concern of spacecraft design. The tax falls most heavily on missions requiring return. Sending a spacecraft on a one-way journey costs 1 set of delta-V requirements. The vehicle launches, travels to its destination, and remains there permanently. It pays the tax only in one direction. Bringing it back costs another complete set of delta-V expenditure. The return journey requires propellant. That propellant has mass. That mass must travel to the destination before it can be used for return. Every kilogram of return propellant pays the outbound tax before it can pay the return tax. This compounding creates severe penalties for round-trip missions. Every kilogram intended to return must carry not just its own mass but all the propellant needed for the return journey. And that return propellant must be launched from Earth in the first place, paying the full ascent tax before even beginning the outbound mission. The mathematics roughly double the difficulty of any round-trip mission compared to one-way travel. Not because the distance doubles, but because the propellant requirements cascade through both directions. This asymmetry explains why robotic exploration has vastly outpaced human exploration of the solar system. Robots need not return. We send them on one-way journeys to distant destinations, accepting that they will remain there until they cease functioning. The Voyager spacecraft launched in 1977 will never come home. The Cassini probe orbited Saturn for 13 years before intentionally plunging into the planet's atmosphere. One-way robotic missions require delta-V budgets roughly half those needed for round trips with equivalent destinations. The equation punishes them only once instead of twice. This makes robotic exploration of distant destinations feasible when human exploration remains extraordinarily difficult. Humans are generally expected to return. Astronauts are not considered expendable resources to be deposited on distant worlds and abandoned. Any serious human exploration program must account for bringing the explorers home. Mars illustrates this challenge with uncomfortable clarity. Getting to Mars requires significant delta-V. The transfer orbit demands departure velocity from Earth, coast through interplanetary space, and arrival velocity management at Mars. Landing on the Martian surface requires additional delta-V to descend through the thin atmosphere and touch down safely. A one-way robotic lander might require total delta V of approximately 11 to 13 kilometers per second from low Earth orbit. This is demanding, but achievable with careful mission design. A human mission that returns the crew requires all of that outbound delta V, plus ascent from the Martian surface, departure from Mars orbit, return transit to Earth, and arrival management back home. The total delta V budget exceeds 25 kilometers per second, roughly double the one-way requirement. That doubling does not translate into doubled mass requirements. The exponential relationship means the mass requirements more than quadruple. The additional delta V for return, applied through the rocket equation, escalates the necessary mass to levels that strain practical capability. Estimates for human Mars missions suggest departure masses from low Earth orbit ranging from 500 metric tons to over 1,000 metric tons, depending on mission architecture and assumptions. Those masses must first be delivered to low Earth orbit from Earth's surface, requiring many times more mass at launch. A minimal human Mars mission might require total launch mass from Earth's surface measured in tens of thousands of metric tons. For comparison, the International Space Station, assembled over more than 2 decades through dozens of launches, has a total mass of approximately 420 metric tons. A single Mars mission would require launching the equivalent of dozens of space stations. No matter the destination, the math does not change. The Moon required the Saturn V, the largest rocket ever successfully flown, to accomplish round-trip human missions. The delta V budget demanded that scale of vehicle. Mars requires something considerably larger, or a fundamentally different approach to mission architecture, to accomplish equivalent human missions. The delta V budget permits no alternative. The outer planets remain effectively unreachable for human crews, using anything resembling current propulsion technology. The delta V budgets exceed what any practical chemical rocket system can provide, with acceptable payload fractions. The equation has already closed those destinations to human exploration. What makes this particularly challenging, particularly inescapable, is that delta V requirements are not arbitrary numbers chosen by engineers. They emerge from orbital mechanics. They derive from the geometry of gravitational wells. They follow from the immutable physics of celestial motion. You cannot negotiate with Jupiter's gravity. The planet masses what it masses, creates the gravitational field it creates, and demands the delta V it demands from any spacecraft seeking to orbit or land. No amount of clever engineering changes what Jupiter requires. You cannot convince Mars to accept less delta V for orbital insertion. The planet's mass determines its gravitational influence. The spacecraft's approach velocity determines how much slowing is required. Physics sets these values, not human preference. The destinations demand what they demand based on fundamental physical relationships. The rocket equation translates those demands into mass requirements. Engineers can optimize within this framework. They can design more efficient trajectories. They can use gravitational assists to borrow momentum from planetary encounters. They can time missions to take advantage of favorable alignments. These efforts produce real improvements, sometimes significant ones. Gravitational assists can reduce mission delta V by substantial amounts. Careful trajectory design can shave kilometers per second from requirements. Aerobraking at destinations with atmospheres can replace some propulsive braking with atmospheric drag. But no optimization removes the fundamental relationship. Every mission still pays tribute to exponential mathematics. Every spacecraft still carries mass ratios determined by velocity requirements. The prison walls can be pushed back slightly through clever engineering. They cannot be removed. This is the exponential prison of space travel. Each increment of capability demands not linear growth, but exponential growth in the machinery required to achieve it. Twice, the delta V does not mean twice the rocket. It means the rocket squared. 3 times the delta V means the rocket cubed. The relationship is relentless, compounding, ultimately crushing to ambitions that ignore it. Each additional destination, each extension of human reach, Each new world we might wish to visit enters this same accounting system. The equation permits no bargaining. It accepts no appeals for mercy. It enforces its constraints with absolute consistency across every mission ever flown and every mission ever proposed. The equation permits reaching low Earth orbit routinely, at enormous cost per kilogram, but with reliable and repeatable technology. The equation permits reaching the Moon with extraordinary vehicles purpose-built for that mission, at costs measured in significant fractions of national GDP. The equation makes reaching Mars with humans extraordinarily difficult, potentially achievable with massive international effort, but certainly not routine. The equation effectively prohibits human travel to the outer solar system with any propulsion technology that expels mass to generate thrust. These are not engineering limitations awaiting clever solutions. These are not budget constraints that additional funding could remove. These are mathematical boundaries that follow from physics itself. Every workaround still answers to the same rule. The chapters that follow will examine proposed solutions to these constraints. Better engines that achieve higher exhaust velocities, larger rockets that accept the mass ratios and scale upward, reusable systems that reduce costs through reflight, nuclear propulsion that offers improved performance over chemical systems. Each of these proposals offers genuine benefits. Each encounters the same mathematical relationship. Each discovers that the rocket equation accommodates improvement while maintaining fundamental dominance over what we can achieve. The prison permits good behavior to earn certain privileges. It does not permit escape. Surely better engines could solve this problem. Surely human ingenuity, the same force that split the atom and decoded the genome and connected billions of minds through invisible signals, could find a way around a simple mathematical relationship. Surely somewhere in the vast landscape of possible technologies lies an engine that defeats the exponential penalty, that transforms space travel from an exercise in diminishing returns into something more reasonable. This hope drives enormous investment in propulsion research. Space agencies around the world fund programs exploring advanced engine concepts. Universities study exotic physics that might someday enable entirely new forms of thrust. The dream of a breakthrough propulsion system that transforms space travel, economics, motivates careers, and consumes budgets measured in billions of dollars. The rocket equation waits patiently for each proposed solution, examines it according to the same mathematics Tsiolkovsky derived more than a century ago, and renders its verdict. So far, that verdict has been consistent. Every propulsion system that expels mass to generate thrust must answer to the same arithmetic. The equation accommodates improvements while maintaining its fundamental constraint. Understanding why requires examining how the equation actually works, what variables it contains, and what happens when engineers attempt to manipulate those variables in their favor. The rocket equation contains exhaust velocity as a key parameter. This variable measures how fast an engine expels its combustion products or reaction mass. Faster exhaust velocity means more thrust per unit of propellant consumed. It means higher efficiency in converting propellant mass into spacecraft velocity. Increase exhaust velocity, and the required mass ratios decrease. This is mathematically true. It is also insufficient to escape the equation's grip. Exhaust velocity, often expressed through a related quantity called specific impulse, measures how effectively an engine converts propellant into useful thrust. The exhaust velocities achievable by chemical rockets represent fundamental limits set by thermodynamics. The chemistry dictates the energy available. The physics dictates how that energy converts to exhaust velocity. No clever engineering dramatically improves these numbers. Ion engines operate on entirely different principles. Instead of burning propellants chemically, they accelerate ionized atoms using electric fields. The ions exit the engine at velocities far exceeding chemical combustion products. Modern ion engines achieve exhaust velocities above 30 km per second. Advanced designs under development might reach 60 or 70 km per second. The difference spans an order of magnitude. Ion engines produce exhaust moving 10 to 20 times faster than chemical rocket exhaust. This seems like it should transform the economics of space travel. If higher exhaust velocity reduces mass ratios, surely 10 times higher exhaust velocity should reduce them by a factor of 10. The mathematics tell a different story. The rocket equation relates exhaust velocity to delta V through a natural logarithm. Increasing exhaust velocity by a factor of 10 does not reduce the required mass ratio by a factor of 10. The improvement is real but diminished by the mathematical structure of the relationship. Consider a spacecraft requiring 20 kilometers per second of delta V, roughly what a human Mars mission demands for the round trip. With typical chemical propulsion, the mass ratio required exceeds 140. The spacecraft must begin weighing 140 times what it weighs at the end. 140 to 1. 99.3% of the vehicle consists of propellant. The payload fraction has collapsed to less than 1%. The spacecraft has become essentially a flying fuel tank with a tiny capsule attached. Now imagine an ion engine with exhaust velocity of 40 kilometers per second, 10 times better than chemical propulsion. Apply the same 20 kilometers per second delta V requirement. The mass ratio drops to approximately 1.65. The spacecraft now needs only 65% additional mass as propellant. The payload fraction has climbed to more than 60%. This appears to be a dramatic revolutionary improvement, from 99% propellant to 40% propellant, from mass ratio of 140 to mass ratio of less than 2. The ion engine seems to have demolished the constraints that make chemical rockets so limited, but the improvement comes with devastating, mission-killing limitations that the mathematics alone do not reveal. Ion engines produce minuscule thrust compared to chemical rockets. A large chemical engine might produce millions of newtons of thrust, enough to lift thousands of tons against Earth's gravity. A large ion engine produces fractions of a newton, barely enough to lift a piece of paper against Earth's gravity. This is not a temporary engineering limitation awaiting solution. It reflects the fundamental physics of how ion engines work. Ion engines accelerate their reaction mass to very high velocities, but they can only process tiny amounts of that mass per second. The electric fields that accelerate ions require enormous power to move significant quantities of material. The ion beams themselves would destroy the engine if made too intense. The physics trades exhaust velocity against mass flow rate. You can have one or the other, but not both simultaneously. Chemical rockets work differently. They process enormous quantities of propellant every second, expelling tons of combustion products in the time an ion engine expels milligrams. The lower exhaust velocity is compensated by the vastly higher mass flow rate, producing thrust levels that can lift vehicles against gravity. An ion engine, with its remarkable exhaust velocity, cannot lift a spacecraft off Earth's surface. It cannot even accelerate fast enough to execute the precise maneuvers required for many mission phases. It cannot slow down quickly when approaching a planet. It cannot perform the rapid orbital adjustments that mission safety often requires. Ion engines accumulate their impressive delta V over months and years of continuous operation. Where a chemical rocket produces thousands of meters per second of velocity change in minutes, an ion engine produces the same change over extended periods of patient, gradual acceleration. This limitation confines ion propulsion to specific mission types. Deep space probes operating on timescales of years can use ion engines effectively. The Dawn spacecraft visited multiple asteroids using ion propulsion, slowly spiraling between destinations over mission durations measured in years. Bepi Colombo spirals toward Mercury on electric thrust. These missions would be impossible with chemical rockets alone. Ion propulsion enabled them precisely because the high exhaust velocity reduced propellant requirements to manageable levels. The technology has proven tremendously valuable within its operational envelope. But ion engines cannot replace chemical propulsion for missions requiring rapid acceleration. They cannot operate effectively near strong gravitational fields, where slow acceleration allows gravity to recapture spacecraft. They cannot provide the thrust-to-weight ratios necessary for landing on worlds with significant gravity. They cannot perform emergency maneuvers when mission safety demands rapid response. The rocket equation still governs ion propulsion. The equation cares about exhaust, velocity, and mass ratio. It does not care how long the acceleration takes. An ion engine still converts delta-V requirements into propellant requirements according to the same mathematics. The mass ratios are more favorable, but mass ratios still exist. The dream of combining high exhaust velocity with high thrust remains largely a dream awaiting physics that does not yet exist. Nuclear thermal propulsion offers better performance than chemical systems while maintaining thrust levels adequate for rapid maneuvers. These engines heat propellant by passing it through a nuclear reactor rather than by chemical combustion. The reactor can achieve higher temperatures than chemical flames, and hydrogen heated to extreme temperatures exits the engine faster than combustion products. Nuclear thermal rockets achieve exhaust velocities roughly double what the best chemical rockets manage. Instead of 4.5 kilometers per second, nuclear thermal systems reach 8 or 9 kilometers per second. This improvement translates directly into reduced mass ratios through the rocket equation. The technology is not speculative. It was tested extensively during the 1960s under a program called NERVA, an acronym for Nuclear Engine for Rocket Vehicle Application. American engineers built and fired nuclear rocket engines on test stands in the Nevada desert. The engines worked. They achieved the predicted performance. They demonstrated that nuclear thermal propulsion was technically feasible. The engines produced specific impulse nearly double that of the best chemical rockets of the era. They generated thrust levels adequate for crewed spacecraft. They operated reliably through multiple test firings. The program accumulated hundreds of thousands of seconds of engine runtime. Nuclear thermal propulsion moved from theory to demonstrated capability. Yet the program was cancelled before any nuclear rocket flew an actual mission. Budget priorities shifted. The Apollo program ended. Political will for ambitious space exploration evaporated. The tested hardware went into museums, while the expertise dispersed into other careers. Why did nuclear propulsion not transform spaceflight, despite its demonstrated advantages? Why did the improvement not change the fundamental economics that make deep space exploration so difficult? The answer lies in what the rocket equation actually permits versus what our intuitions expect. Doubling exhaust velocity does not halve the mass ratio for a given mission. The logarithmic relationship in the equation compresses the benefit. Doubling exhaust velocity roughly halves the exponent in the mass ratio calculation, which helps significantly but not transformatively. A mission requiring a mass ratio of 140 with chemical rockets might require a mass ratio of around 12 with nuclear thermal propulsion. 12 is dramatically better than 140. A spacecraft that was 99% propellant becomes roughly 90% propellant. The payload fraction improves from less than 1% to perhaps 8 or 9%. This represents substantial improvement. Missions that were barely possible with chemical propulsion become more practical with nuclear thermal systems. Mass that would have been propellant can become payload. Spacecraft can carry more equipment, more supplies, more capability, but 12 is not one. The spacecraft still begins the journey weighing 11 times what it weighs at the end. Propellant still dominates the mass budget. The equation still extracts its toll, just at a reduced rate. Nuclear thermal propulsion operates within the same mathematical framework as chemical rockets. It shifts the numbers favorably, but does not escape the exponential relationship. Every kilogram of payload still requires multiple kilograms of propellant to reach distant destinations. The tax rate is lower, but the tax remains. Nuclear electric propulsion combines nuclear power generation with ion engines, achieving the high exhaust velocities of electric propulsion while avoiding the need to carry solar panels into the outer solar system where sunlight grows dim. A nuclear reactor generates electricity that powers ion engines for years of continuous operation. The spacecraft slowly accelerates to tremendous velocities over extended mission durations. This approach enables missions to distant destinations that would otherwise be completely impossible. Robotic probes to the outer planets and beyond become feasible when nuclear electric systems provide the delta V. Journey times remain long, but the destinations become reachable. But nuclear electric propulsion shares the fundamental limitations of all electric propulsion. Low thrust requires trip times measured in years. The spacecraft cannot operate effectively near strong gravitational fields. It cannot perform rapid maneuvers when mission requirements demand quick response. The propulsion system enables certain mission types while remaining unsuitable for others. Some proposals throughout history have suggested nuclear pulse propulsion, using sequential nuclear explosions to push a spacecraft. Project Orion explored this concept in the 1950s and 60s with surprising rigor. Engineers calculated that carefully shaped nuclear charges, detonated behind a massive pusher plate attached to the spacecraft through shock absorbers, could accelerate large payloads to tremendous velocities. The physics appeared sound. The engineering seemed achievable with the technology of the era. Project Orion calculated that nuclear pulse propulsion could achieve exhaust velocities exceeding 20 kilometers per second while maintaining thrust levels capable of lifting spacecraft from Earth's surface. This combination of high exhaust velocity and high thrust would genuinely transform space travel economics if it could be implemented. Small-scale tests using conventional explosives demonstrated that the pusher plate concept worked. The calculations suggested that nuclear implementation would scale appropriately. Serious engineers at serious institutions devoted years to developing the concept. But nuclear pulse propulsion would create radioactive fallout with each launch. Detonating nuclear weapons in the atmosphere, even for propulsion purposes, violates test ban treaties that the United States and other nations signed for compelling reasons. The environmental consequences of routine nuclear pulse launches would be severe and unacceptable. The concept remains confined to theoretical discussions and science fiction, not because it violates the rocket equation, but because it violates international law, basic environmental responsibility, and any reasonable assessment of acceptable risk. Every proposed propulsion improvement encounters the same pattern. The rocket equation accommodates the improvement, calculates new mass ratios according to the same mathematics, and renders a verdict that is better but not fundamentally different. Better engines reduce mass ratios without eliminating them. Faster acceleration comes at the cost of lower exhaust velocity. Higher exhaust velocity requires accepting lower thrust. The equation permits no combination that escapes its framework. Perhaps bigger rockets could overcome these limits through brute force rather than elegance. If mass ratios remain severe, regardless of propulsion technology, simply start with more mass. Build larger vehicles, carry more propellant, accept the proportions and scale upward until useful payloads reach sizes adequate for ambitious missions. This approach encounters problems that compound faster than capabilities grow. Structural mass scales unfavorably with size. When you double the linear dimensions of a structure, its volume increases by a factor of 8, because volume scales with the cube of linear dimension. The weight of propellant the structure must contain increases 8-fold, but the structural strength increases only by a factor of 4, because strength scales with the square of linear dimension proportional to the cross-sectional area of structural members. Double the size and you have 8 times the load supported by 4 times the strength. The structure must become proportionally heavier to compensate. Thicker walls, stronger supports, more mass devoted to holding things together rather than accomplishing mission objectives. This scaling relationship creates practical limits on how large rockets can grow. Beyond a certain size, the structural mass required to support the vehicle consumes more and more of the total mass budget. Payload fraction, already small due to propellant requirements, shrinks further as structure grows. The Saturn V approached practical limits for chemical rocket size. Its structural mass fraction pushed against what materials science could achieve, and scaling significantly larger would have required exotic materials and construction techniques that did not exist. Modern heavy-lift rockets like Falcon Heavy and the Space Launch System represent incremental improvements on those capabilities, not dramatic expansions beyond them. Decades of advancement have enabled some growth, but no rocket currently flying or seriously planned significantly exceeds the Saturn V in payload capability to deep space destinations. The fundamental scaling constraints remain. Building rockets 10 times larger would require engineering breakthroughs that do not currently exist. Structural materials with strength-to-weight ratios beyond current capabilities, manufacturing precision at scales never achieved. The scaling limits are real. Some engineers argue these breakthroughs might eventually occur. Materials science continues advancing. Manufacturing capabilities continue improving. Perhaps someday rockets 10 times larger than Saturn V will become possible. But even if such vehicles could be built, the rocket equation would still apply. A larger rocket with the same exhaust velocity and delta-v requirement needs the same mass ratio as a smaller one. Scaling up delivers proportionally larger payloads, but does not change the fundamental economics. If 90% of a small rocket is propellant, 90% of a large rocket will also be propellant. Size does not defeat the equation. Size merely allows accomplishing with one enormous vehicle what would otherwise require multiple smaller ones. The physics remains unchanged. What about reusability? The space industry has undergone a revolution in recent years, as companies demonstrated routine recovery and reuse of rocket hardware that was previously discarded after single flights. Boosters that once fell into the ocean now land on drone ships and launch pads, ready for refurbishment and reflight. This revolution has dramatically reduced the cost of reaching orbit. When expensive hardware returns for reuse instead of being thrown away, the economics improve substantially. What once cost hundreds of millions of dollars per launch can now cost tens of millions. Access to low Earth orbit has become more affordable than at any previous time in history. Perhaps reusability transforms the economics of deep space exploration in the same way it has transformed access to Earth orbit. It does not. Reusability addresses economics, not physics. A reusable rocket still requires the same mass ratio to reach orbit as a disposable one. It still burns the same propellant per kilogram of payload delivered. It still obeys the same mathematical relationship between delta-v requirements and propellant mass. The savings from reusability come from not discarding expensive hardware, not from changing the underlying physics. The rocket equation does not care whether the engines and tanks that lift a payload to orbit are subsequently recovered or abandoned. It cares only about mass ratios and exhaust velocities and velocity changes. For missions beyond low Earth orbit, reusability becomes increasingly difficult to apply meaningfully. A rocket stage that delivers payload to translunar trajectory acquires significant velocity in the Earth departure direction. Returning that stage to Earth for reuse requires reversing that velocity, a process that consumes substantial propellant and adds substantial complexity. Some architectures propose refueling reusable stages in orbit, allowing them to be used repeatedly for deep space departures. This helps with economics, but not with physics. The propellant for those refueling missions must still be launched from Earth's surface, paying the full ascent tax. The total propellant requirement for the mission remains unchanged regardless of whether it launches on expendable or reusable vehicles. A spacecraft that travels to Mars cannot reasonably return to Earth for refurbishment before its next mission. The delta-v requirements for the return journey are severe. The time for the return trip adds months or years to mission schedules. Reuse of interplanetary spacecraft makes no practical sense with current or foreseeable technology. Reusability works best for the portion of space missions where hardware remains near Earth. It reduces the cost of the first step while leaving subsequent steps unchanged. For missions where that first step dominates costs, reusability transforms economics. For missions where deep space segments dominate challenges, reusability helps less. The rocket equation continues, extracting its heaviest toll on the portions of missions where reusability cannot easily apply. In situ resource utilization has been proposed as a way around the equation's constraints for certain destinations. Instead of carrying all propellant from Earth, manufacture propellant at the destination using local resources. Reduce the mass that must be launched from Earth by producing what you need after arrival. The concept has genuine merit for specific mission architectures. Mars has an atmosphere composed primarily of carbon dioxide. Chemical processes can convert that carbon dioxide into methane and oxygen, propellant suitable for rocket engines. A Mars mission that manufactures its return propellant on the Martian surface avoids carrying that propellant from Earth. The mass savings can be substantial. The Moon has water ice in permanently shadowed craters near its poles. That water can be split into hydrogen and oxygen through electrolysis. Liquid hydrogen and liquid oxygen form an excellent propellant combination. A lunar base that produces its own propellant could dramatically reduce supply requirements from Earth. Asteroids contain various materials that might serve as propellants or propellant feedstocks. Space-based infrastructure that harvests asteroidal resources might eventually enable activities impossible when everything must be launched from Earth. These are not fantasies. The chemistry is well understood. Prototype systems have demonstrated key processes. Mission architectures incorporating in-situ resource utilization have been studied in detail by space agencies and private companies, but in-situ resource utilization does not escape the rocket equation. It changes where the equation's toll is paid, not whether payment is required. Manufacturing propellant on Mars requires equipment that must be delivered from Earth. Chemical processing plants, power systems, storage tanks, all the infrastructure of propellant production. That equipment has mass. That mass must be launched from Earth's surface, paying the full ascent tax. It must be transported to Mars, paying the interplanetary transit tax. The manufactured propellant itself still obeys the rocket equation. Using Mars-produced methane and oxygen to launch from the Martian surface requires mass ratios determined by Martian gravity and engine exhaust velocity. The propellant may have been manufactured locally, but the physics of using it remains unchanged. Furthermore, in-situ resource utilization only helps for destinations where suitable resources exist and can be economically processed. Not every destination offers convenient feedstocks. Not every resource can be extracted with reasonable equipment mass. The approach works for some missions to some destinations. It does not represent a universal solution. Most critically, in-situ resource utilization cannot help during transit phases of missions. Interplanetary space offers nothing to refuel with. The journey between Earth and Mars, during which most of the mission Delta-V must be expended, provides no opportunity for local resupply. The spacecraft must carry all the propellant needed for the transfer, or preposition that propellant through additional launches. The equation governs transit segments without any possibility of escape through local resources. A Mars mission might manufacture return propellant on the surface, but it cannot manufacture outbound propellant during the cruise phase. That propellant must come from Earth regardless of what happens at destination. Every workaround still answers to the same rule. Better engines reduce mass ratios but cannot eliminate them. The improvement is real, but bounded. No propulsion system that expels mass can escape the fundamental relationship between exhaust, velocity, delta-V, and mass ratio. Larger rockets face scaling limits that constrain practical size. Beyond certain dimensions, rockets become impractical regardless of technology improvements. Reusability cuts costs without changing physics. The economic benefits are substantial, but do not affect the underlying mass ratios that determine what missions are possible. Resource utilization helps at destinations, but not during transit. The approach enables certain mission architectures while leaving others unchanged. Each proposed solution achieves real benefits while remaining firmly within the mathematical framework the rocket equation establishes. The solutions are not worthless. They are genuinely valuable. They expand what humanity can accomplish in space. They make difficult missions possible, and impossible missions merely extraordinarily difficult. But they do not transform the fundamental economics. They do not defeat the exponential penalty. They do not change the underlying reality that propelling mass through space requires carrying propellant that itself must be propelled. The distinction between engineering cleverness and physical permission becomes crucial here. Engineering cleverness finds ways to accomplish objectives more efficiently within physical constraints. It optimizes trajectories, reduces structural mass, improves engine performance, recovers, and reuses hardware. Engineering cleverness has made space exploration possible and continues to expand what we can achieve. Physical permission determines what is possible at all. It establishes the boundaries within which engineering cleverness operates. The rocket equation establishes physical permission for reaction propulsion. It determines what mass ratios any propulsion system must accept. It sets limits that no amount of engineering cleverness can transcend. No amount of clever engineering changes the relationship between delta-v requirements and propellant mass for systems that generate thrust by expelling reaction mass. The relationship is mathematical and applies universally to any system operating on reaction principles. Space agencies and aerospace companies continue developing better propulsion systems. These efforts will produce real improvements in what humanity can accomplish. Chemical rockets will become somewhat more efficient as engine designs are refined. Electric propulsion will enable missions previously impossible due to propellant constraints. Nuclear systems may eventually fly operational missions and transform certain categories of space activity. But these improvements operate within boundaries the equation has already established. They push back the walls of the possible without removing those walls entirely. The equation is the quiet limiter beneath every mission, permitting some ambitions while denying others, shaping what space exploration can realistically accomplish. This is the illusion of solutions. Each proposed improvement appears to offer escape from current limitations. Each seems to promise transformation of space travel economics. Each generates enthusiasm and investment, and hope that the fundamental constraints might finally yield. Each encounters the same mathematical relationship that governed the first rockets and will govern the last. The equation survives every innovation, adapts its constraints to new propulsion technologies, and maintains its essential character regardless of how cleverly engineers manipulate its variables. The equation does not prevent progress. Progress continues. Capabilities expand. Missions that would have seemed impossible a generation ago now fly routinely. This progress is real and valuable and worth celebrating. But the equation channels that progress along particular paths while blocking others entirely. It permits certain categories of achievement while forbidding others. It allows incremental expansion of human reach while preventing transformative change in the fundamental economics of space travel. This is the quiet limiter beneath every mission. Robotic exploration of the outer solar system is possible because robots need not return. They pay the equation's toll in one direction only. They accumulate delta-v over extended periods using efficient electric propulsion. They accomplish their missions without carrying the propellant for return journeys. Human exploration of Mars is conceivably possible because the delta-v requirements, while severe, fall within what enormous vehicles launched by the largest rockets might achieve. The equation permits Mars missions. It simply demands a price so high that such missions remain rare if they occur at all. Human exploration of the outer planets remains effectively impossible because the delta-v requirements exceed what any currently conceivable propulsion system could supply with acceptable mass ratios. The equation has already rendered its verdict on Jupiter and Saturn and the ice giants beyond. Human visits to those worlds await propulsion technologies that do not currently exist and may never exist within the framework of reaction, propulsion, These are not temporary limitations awaiting future solutions. They are consequences of physics that no technology operating on reaction principles can circumvent. The mathematics are clear. The constraints are real. But we have not yet confronted what these constraints truly mean. Not for individual missions or specific technologies, but for the scope of human activity beyond Earth, for our reach within the solar system, for the dream of travelling to other stars. The equation has rendered its verdict on all of these ambitions. We must now understand what that verdict contains. Every workaround still answers to the same rule, and the rule defines a ceiling we cannot raise. Now, we must confront what this single mathematical relationship means for the scope of human activity beyond Earth. Not what we hope it means, not what science fiction suggests it might mean, what it actually means when examined honestly. Without the comforting illusions that permeate most discussions of humanity's cosmic future, the rocket equation does not merely make space travel difficult. Difficulty implies challenge that effort can overcome. The equation does something more fundamental. It establishes a ceiling on what is practically achievable, a boundary between what we can realistically accomplish and what physics simply will not permit, no matter our determination, funding, technological sophistication, or dreams. This ceiling operates invisibly in most public discussions of space exploration. Politicians announce bold visions of Mars colonies. Entrepreneurs promise settlements throughout the solar system. Futurists describe humanity spreading among the stars. These visions proceed as if sufficient ambition and investment can overcome any obstacle, as if space travel difficulties represent merely the current state of technology rather than permanent features of physical reality. The equation suggests otherwise. It suggests that certain objectives face barriers no conceivable technology operating on reaction principles can surmount. It suggests that other objectives face costs so severe that pursuing them becomes questionable from any rational perspective. It suggests that our cosmic reach has limits we did not choose and cannot change. Consider the practical boundaries of human spaceflight within our own solar system. These boundaries emerge not from engineering limitations or budget constraints, but from the mathematics governing how rockets work. The moon lies within reach. This is demonstrated fact, not hopeful projection. The Apollo program proved conclusively that human beings can travel to the lunar surface and return safely. The delta-V requirements for lunar missions, while demanding, fall within what staged chemical rockets can achieve with payload fractions adequate for meaningful missions. The equation permits lunar exploration. It extracts an enormous toll in mass and cost, but it does not forbid the journey. 12 human beings walked on the moon between 1969 and 1972. They travelled there aboard the largest rockets ever successfully flown. Vehicles that represented the absolute limit of what 1960s technology could achieve. The missions cost, in inflation-adjusted terms, hundreds of billions of dollars. They required mobilizing significant fractions of national industrial capacity. They demanded accepting risks that would be considered unacceptable by modern safety standards. But the missions happened. The equation permitted them. Human footprints remain in lunar dust, preserved in the airless environment, testament to what the mathematics allow when sufficient resources are committed. Mars presents a far more severe challenge. The red planet lies, not impossibly far, but substantially farther in terms of the currency that actually matters. The delta-V requirements for Mars round trips push mass ratios toward the limits of what staging and propellant fraction can accommodate using any propulsion technology that currently exists or can be reasonably projected. Practical mission designs for human Mars expeditions require launching hundreds of metric tons to low Earth orbit. That mass must be assembled in orbit into vehicles of unprecedented size. Vehicles that dwarf the International Space Station in complexity and exceed the Saturn V in ambition. The transit times stretch to months in each direction. The crew must survive radiation exposure, isolation, and medical emergencies far from any possible rescue. The equation permits this, in principle. It does not absolutely forbid human travel to Mars. It simply demands payment so severe that such missions remain aspirational after decades of discussion. Multiple space agencies have announced Mars ambitions. Multiple target dates have come and gone without missions launching. The gap between announcement and achievement reflects the equation's toll. The enormous difficulty of accumulating enough mass in orbit to satisfy what the mathematics require. Some organizations continue pursuing Mars missions seriously. They study mission architectures. They develop necessary technologies. They accumulate the resources and capabilities that might eventually enable the journey. Perhaps within the coming decades, human beings will finally walk on Martian soil. If they do, they will travel aboard vehicles built to satisfy the rocket equation's demands. They will accept mass ratios that consume most of their departure mass as propellant. They will demonstrate not that the equation can be defeated, but that extraordinary effort can accomplish what the equation permits at extraordinary cost. Beyond Mars, the equation's verdict grows substantially harsher. Jupiter lies 5 times farther from the Sun than Earth. Reaching the Jovian system requires delta-v budgets that make even Mars look accessible by comparison. The velocity changes needed to travel from Earth to Jupiter orbit, land on one of its moons, and return safely to Earth exceed what chemical propulsion can practically provide. Nuclear thermal systems might theoretically enable such missions, but the mass ratios remain punishing. A human mission to Europa or Ganymede, Jupiter's potentially habitable ocean moons, would require capabilities far beyond anything currently under development. Launching thousands of metric tons to low Earth orbit, assembling those thousands of tons into spacecraft requiring years of transit time in each direction, keeping human crews alive and functional through radiation environments far more severe than anything near Earth, providing propulsion for numerous major maneuvers across the mission profile. The numbers become impractical long before they become absolutely impossible. No engineering analysis has produced a viable architecture for human Jupiter missions using any propulsion technology that actually exists. The theoretical studies that have been conducted reveal mass requirements so extreme that they border on absurdity, demanding launch capabilities that would require decades of infrastructure development to achieve. Saturn lies twice as far from the Sun as Jupiter. Uranus lies twice as far as Saturn. These ice giants and their moons, worlds that harbour some of the most intriguing environments in our solar system, remain effectively unreachable for human crews using any propulsion technology that obeys the rocket equation. The delta-v requirements exceed what nuclear thermal propulsion can provide, with mass ratios that leave room for meaningful payload. The transit times stretch into decades, longer than the professional careers of the engineers who might design such missions. The radiation exposure, the life support requirements, the psychological challenges of years-long isolation, all compound difficulties that begin with the equation's fundamental constraint. The mathematics do not absolutely forbid human travel to the outer planets. Mathematics makes no absolute prohibitions. A spacecraft with mass ratio of 10,000 to 1 is mathematically possible, even if practically absurd. But the equation makes outer planet missions so difficult that no serious engineering study has ever produced a viable architecture, and none seems likely to emerge within any reasonable planning horizon. This creates a de facto boundary around the inner solar system. Humans might conceivably reach Mars and its moons. We might establish some form of sustained presence on the moon. But the outer solar system remains the province of robotic probes, machines that need not return, that can tolerate years of travel, that require no food or water or oxygen, that can be designed to survive radiation environments that would kill human crews. The equation divides our solar system into zones of human accessibility and zones reserved for our mechanical representatives. This division emerges not from current technological limitations, but from physics itself. No foreseeable advancement changes the fundamental relationship between delta-v requirements and mass ratios. The zones may shift at their boundaries as propulsion technology improves, but the basic division will persist. Voyager crossed the outer solar system because it did not need to return. Cassini orbited Saturn for 13 years because no human crew awaited rescue. New Horizons flew past Pluto because it could tolerate a decade of cruise without life support or psychological intervention. These achievements represent the equation permitting one-way robotic journeys, while effectively prohibiting round-trip human expeditions to the same destinations. The equation's implications become still more profound, still more constraining, when we turn our attention from the solar system to the stars. The nearest star system, Alpha Centauri, lies approximately 4 light-years away. 4 light-years means that light itself, travelling at the universal speed limit, requires 4 years to make the journey. Any spacecraft travelling slower than light, which means any spacecraft that obeys known physics, requires longer. Consider what reaching Alpha Centauri would actually require. The distance measures roughly 40 trillion kilometers. A spacecraft travelling at the velocity of the Voyager probes, currently the fastest human-made objects relative to the Sun, would require approximately 70,000 years to reach Alpha Centauri. 70 millennia. Longer than the entire span of human civilization. Longer than the time since humans first painted on cave walls. Reducing that travel time requires higher velocities, dramatically higher velocities. Velocities that transform the rocket equation from merely punishing to absolutely prohibitive. Consider a spacecraft travelling at 1% of light speed. This velocity, approximately 3,000 kilometers per second, represents speeds far beyond anything human technology has ever achieved. The fastest spacecraft ever launched, the Parker Solar Probe, briefly reaches around 190 kilometers per second during its closest approaches to the Sun, though it cannot maintain such speeds in deep space. The Voyager probes, our farthest travellers, cruise at roughly 17 kilometers per second. At 1% of light speed, the journey to Alpha Centauri takes approximately 400 years, still impossibly long for human crews, but at least falling within the span of recorded history. A civilization that launched such a spacecraft might still exist when it arrived, might still be capable of receiving whatever data it transmitted back. Achieving 1% of light speed requires delta V of approximately 3,000 kilometers per second. Compare this to the roughly 20 kilometers per second needed for a Mars round trip. The interstellar journey demands delta V, 150 times greater. Run those numbers through the rocket equation. Apply any exhaust velocity achievable by any propulsion system humans have ever built, ever tested, ever seriously proposed. The mass ratios that emerge exceed comprehension. A spacecraft using the best chemical propulsion would need a mass ratio exceeding 10 to the 290th power. This number is not merely large, it is meaningless. It exceeds the number of atoms in the observable universe by factors that themselves exceed the number of atoms in the observable universe. Nuclear thermal propulsion improves the situation, but not nearly enough. With exhaust velocity of 9 kilometers per second, the mass ratio required still exceeds 10 to the 145th power, still meaningless. Still vastly beyond the matter content of the cosmos. Even nuclear pulse propulsion, the theoretical system using nuclear explosions for thrust, cannot help. With optimistically projected exhaust velocities of 20 kilometers per second, the mass ratio for 1% of light speed still exceeds 10 to the 65th power. This number is approximately equal to the total number of atoms in the observable universe. The entire mass content of everything we can see would need to serve as propellant for a single spacecraft. The equation pronounces its verdict on interstellar travel with unmistakable clarity. Using propulsion systems that expel mass to generate thrust, travelling to even the nearest stars at significant fractions of light speed is not merely difficult. It is not merely extraordinarily challenging. It is not merely beyond current technology. It is physically impossible, regardless of any technological advancement that operates within the same framework. The mathematics forbid it absolutely. This does not mean interstellar travel is impossible by other means. The equation governs reaction propulsion specifically, systems that generate thrust by expelling mass. Other approaches might circumvent its constraints. Laser sails pushed by ground-based or space-based beam stations could theoretically achieve significant fractions of light speed for very small payloads. The Breakthrough Starshot initiative proposes sending gram-scale probes to Alpha Centauri, using powerful lasers to accelerate tiny spacecraft equipped with reflective sails. Such probes would not carry propellant. They would not generate thrust by expelling mass. They would operate outside the framework the rocket equation governs. But laser sails face their own severe limitations. The payloads must be extraordinarily small to achieve useful velocities. The beam stations must be impossibly powerful by current standards. The probes cannot slow down at their destinations without propellant, meaning they flash through the target system in hours, gathering what data they can during a brief encounter. The approach might enable flyby reconnaissance of nearby stars. It cannot enable human travel or sustained presence. Other theoretical concepts exist on paper. Solar sails that ride the pressure of sunlight, magnetic sails that push against the interstellar medium, antimatter propulsion that achieves exhaust velocities approaching light speed. Each concept encounters its own limitations, its own physical constraints, its own reasons why interstellar travel remains beyond practical reach. For spacecraft that carry their own propellant, that generate thrust by ejecting mass, the rocket equation forbids interstellar travel at relativistic speeds. Period. No exceptions. No workarounds. No breakthroughs waiting to be discovered. The mathematics are clear, and mathematics does not negotiate. The rocket equation thus defines the character of any spacefaring civilization that relies on reaction propulsion. This includes human civilization. This likely includes any alien civilization that develops technology through similar pathways. Such civilizations can explore and perhaps colonize their local planetary systems. They can expand through their inner solar systems at enormous cost. They can send robotic probes to outer planets, on journeys measured in years. They can establish presences on moons and asteroids that fall within the equation's permitted range. They cannot transport significant payloads between star systems in reasonable timeframes. The equation prohibits this absolutely for any propulsion system operating on reaction principles. The distances are too vast. The velocity requirements are too extreme. The mass ratios become infinite for practical purposes. This mathematical reality may explain something profound about the universe we observe. When astronomers search for signals from extraterrestrial civilizations, they confront what has been called the Fermi paradox. If intelligent life is common in the universe, if civilizations have had billions of years to spread through the galaxy, why do we see no evidence of their presence? Why is the cosmos silent? Where is everybody? The rocket equation suggests an answer. Perhaps the silence exists because interstellar travel is genuinely impossible for civilizations that rely on reaction propulsion. Perhaps alien species throughout the galaxy face the same physical constraints we do. Perhaps they too derived their versions of the rocket equation and discovered the same exponential wall-blocking expansion to the stars. This does not require that intelligent life is rare. It does not require that civilizations inevitably destroy themselves. It simply requires that physics operates the same way everywhere, that the conservation of momentum applies across the cosmos, that the rocket equation governs any species attempting to propel mass through space. Alien civilizations might exist in enormous numbers. They might have developed technologies far surpassing human capabilities. They might have spread throughout their home planetary systems, establishing presences on every accessible world. But the equation would still constrain their expansion just as it constrains ours. The galaxy might be full of spacefaring civilizations, each confined to its home star system, by the same mathematics that confines us. Interstellar communication by electromagnetic signals remains possible. Light speed limits the conversation to exchanges spanning decades or centuries, but information can cross the void even if ships cannot. Each civilization might know that others exist while remaining forever isolated by distances the equation forbids crossing. This is speculation, of course. We have no evidence of extraterrestrial civilizations. We do not know whether the equation truly represents a universal barrier or merely a human limitation that cleverer species have somehow transcended. But the mathematics suggest that any species relying on reaction propulsion faces the same constraints we do. Physics does not play favorites. The rocket equation might represent a universal limiter, constraining all technological civilizations throughout the cosmos to remain largely confined within their birth systems, not because of insufficient ambition or inadequate technology, but because physics itself permits no alternative within the framework of reaction propulsion. Here we arrive at the philosophical implications of living under this constraint. We must confront what it means to exist as beings capable of glimpsing the universe but incapable of freely traversing it. The rocket equation is not a problem awaiting solution. It is not a barrier that sufficient effort will eventually overcome. It is a feature of physical reality, a description of how the universe actually works. The universe makes moving mass through space fundamentally expensive. The cost scales exponentially with desired velocity. This is simply true, verified by every rocket ever flown, enforced by the conservation of momentum that governs all motion in the cosmos. Human technology has developed remarkable capabilities for operating within these constraints. We have built spacecraft that traverse significant portions of the solar system. We have landed robots on worlds millions of kilometers away. We have flown probes past the outer planets and into interstellar space. We have established a continuous human presence in low Earth orbit maintained for more than 2 decades. These achievements required accepting the equation's toll, not circumventing it. Every mission paid the exponential price. Every spacecraft carried propellant loads determined by the mathematics. Every extension of human reach came at costs the equation specified. Future technologies will extend these capabilities further. Better propulsion systems will enable missions currently impossible. Larger infrastructure in space might eventually support more ambitious endeavors. Nuclear propulsion may finally fly and improve mass ratios for certain mission types. In situ resource utilization may reduce Earth launch requirements for certain destinations. The equation permits these improvements. It permits progress within its constraints. It allows expanding human presence in the inner solar system. It allows increasingly sophisticated robotic exploration of destinations humans cannot reach. It allows incremental advancement toward more capable space infrastructure. But the equation also teaches something that human culture rarely acknowledges. It teaches humility. Human beings naturally assume that problems yield to effort. We celebrate overcoming obstacles. We tell stories of impossible goals achieved through determination. We believe, because our experience often confirms, that sufficient cleverness and persistence can transcend any barrier. The rocket equation suggests otherwise. It reminds us that physical law constrains what is possible regardless of desire or determination. Some goals lie beyond reach, not because we lack cleverness or resources, but because reality itself forbids them. This is difficult to accept. It contradicts the narrative of limitless human potential that pervades modern culture. It suggests that certain dreams will remain dreams, regardless of how fervently we pursue them. But accepting this reality is not defeat. It is wisdom. The astronauts who traveled to the moon did not escape the rocket equation. They accepted its terms and built vehicles that satisfied its demands. Every gram of their spacecraft was weighed against the exponential penalty. Every maneuver was planned to minimize velocity requirements. Every design decision acknowledged what the mathematics required. The mission succeeded because engineers worked within the equation's constraints, not because they found ways around them. They accepted reality and accomplished what reality permitted. They did not waste effort pursuing what reality forbade. This is perhaps the deepest lesson the rocket equation offers. There exist hard limits on what any technology can accomplish. These limits emerge from fundamental physics, not from temporary gaps in knowledge. No future breakthrough will change the relationship between mass, exhaust velocity, and delta V. That relationship is fixed by the conservation of momentum, one of the most thoroughly verified principles in all of physics. When a rocket pushes exhaust backward, momentum transfers to the vehicle, pushing it forward. Newton's third law. Action and reaction. This principle underlies every rocket ever built, and every rocket that ever will be built. Conservation of momentum has been tested in countless experiments over centuries. It has never been violated. It applies to every collision, every explosion, every rocket firing, every motion of every object in the universe. To escape the rocket equation would require violating conservation of momentum, would require physics to work differently than all evidence indicates it works. This is not impossible in the way that difficult engineering is impossible. It is impossible in the way that perpetual motion is impossible, in the way that travelling faster than light is impossible. The equation derives from physical law that has never been observed to fail. Confronting these limits honestly changes how we should think about space exploration. It suggests focusing efforts on goals the equation permits, rather than dreaming endlessly about goals it forbids. It suggests celebrating achievements within constraints rather than imagining constraints will someday vanish. It suggests a mature relationship with physical reality that acknowledges what cannot change. Future space exploration will follow the same pattern established by past space exploration. Mars missions, if they occur, will require accepting severe mass ratios and building accordingly. Lunar bases will demand supply chains that account for the equation's toll on every kilogram delivered. Each extension of human presence beyond Earth will negotiate with the same mathematics that governed the first orbital flights. The rocket equation stands as the defining relationship of the space age. It determined what Apollo could accomplish. It shapes what every space agency and private company plans today. It will constrain whatever missions humanity attempts in the centuries and millennia to come. This single formula, derived by Tsiolkovsky in solitary contemplation more than a century ago, governs the practical ceiling of our cosmic reach. He never saw a rocket fly, yet his mathematics remains the governing law of astronautics. We began this exploration by noting that most people have never heard of this equation despite its fundamental importance. Now, we understand why it matters. The equation explains why space travel remains difficult after more than 70 years of continuous effort and development. The difficulty is not temporary. It emerges from physics itself. The equation explains why costs remain high, despite revolutionary improvements in technology and manufacturing. The costs reflect propellant requirements that no technology eliminates. The equation explains why certain destinations remain beyond practical reach, regardless of how ardently we desire to visit them. The desire does not change the mathematics. The universe runs on mathematics. That mathematics does not yield to human preference. The rocket equation encodes a truth about how mass, energy, and momentum relate in our cosmos. Every rocket ever built has paid tribute to this relationship. This is not a tragedy. It is simply the nature of reality. The universe permits some things and forbids others. Space exploration falls into the category of things permitted under severe constraints rather than freely allowed. We can operate in space. We can accomplish remarkable things in space, but we operate on terms the universe dictates, not terms we would choose. Understanding those constraints honestly represents the beginning of wisdom about humanity's cosmic prospects, not false optimism that technology will eventually overcome all barriers, not false pessimism that constraints make effort pointless, wisdom that accepts reality while accomplishing everything reality permits. The equation that limits everything we can do in space will continue limiting everything we do in space. It will not be negotiated away through clever diplomacy with physics. It will not be engineered around through breakthrough technology that violates conservation of momentum. It will not be overcome through heroic determination that bends physical law through sheer will. It will remain the quiet governor of astronautics, the hidden ceiling above our ambitions, the mathematical truth that no future can escape. Every thrilling launch you will ever witness, every mission to the moon or Mars or destinations beyond, every spacecraft that ventures into the darkness between worlds, all of them will answer to this same arithmetic. The equation cares nothing for human drama, human ambition, human dreams. It simply describes how rockets work, and it describes them correctly. The equation wrote itself into the laws of physics long before humans evolved to discover rockets. It existed when dinosaurs walked the earth, and when the first single-celled organisms appeared in ancient oceans. It will remain true long after our species is gone, governing any future beings who attempt to propel mass through the cosmos. This is the final understanding. The rocket equation defines what humanity can accomplish among the stars. It is not the barrier we wish it were, something temporary to be overcome with sufficient effort. It is the barrier that actually exists. The constraint physics actually imposes, the ceiling we actually cannot raise. Understanding this transforms how we see our cosmic future. Not as unlimited potential, waiting to be unlocked through inevitable technological progress. Not as a frontier that will yield to human expansion as terrestrial frontiers have yielded, but as constrained possibility within boundaries we did not choose and cannot change. We are creatures who can glimpse the universe, but cannot freely traverse it. We can send our instruments to distant worlds, but cannot easily follow ourselves. We can dream of stars we can never reach. We live under a ceiling imposed by physics itself, and wisdom begins with accepting what that ceiling means. The rocket equation is not our enemy. It is simply the truth. And truth, however constraining, however disappointing to our aspirations, however limiting to our dreams, deserves our respect and our acceptance. This is the equation that limits everything we can do in space. It always has been. It always will be. And perhaps there is a strange comfort in that permanence. The equation is not arbitrary. It does not change based on politics or economics or fashion. It remains constant, while human affairs fluctuate. It provides a fixed reference point in a universe of uncertainty. The ceiling is real. The ceiling is permanent. The ceiling defines what we are as a spacefaring species. What we accomplish beneath that ceiling, within the constraints the equation imposes, remains our choice. We can accomplish much. We can reach the moon. We can perhaps reach Mars. We can send our robot emissaries throughout the solar system. We can learn the secrets of worlds we will never personally visit. The equation permits all of this. It permits remarkable achievements within its constraints. It permits a meaningful human presence in space, expanding gradually outward through the inner solar system over generations and centuries. It forbids the easy interplanetary travel of science fiction. It forbids routine voyages to the outer planets. It forbids journeys to the stars, using any propulsion system that expels mass to generate thrust. Within what is permitted lies more than enough to occupy humanity for as long as our species endures. The constraint is real, but what remains possible after accounting for that constraint is vast. The rocket equation defines our ceiling. What we build beneath that ceiling remains up to us.